So, in the realm of infinite series, there's one type of series that is particularly important and particularly special. This is something called a geometric series. Right? This series here shows up in lots of places. For example, one place it shows up is when you're looking at compound interest. Right? You get this kind of geometric growth. Right? So what's going on here? Right? What we're going to do is we're going to say pick a number a that is not 0 and just some number r. This is going to be, these are both real numbers. Right? And the sequence I want you to consider this time is the sequence a times r squared, a times r cubed, and so on. Right? So, if we look at this here, this is called a geometric sequence. Right? What we have here is this number r. This is called the ratio. Because if we take two consecutive terms and divide them, the ratio of that is r. Right? This is the ratio of one term to the next. Right? Here, our general term, we're actually not going to start our index at 1 this time. We're going to say a0 is a. A is a little unfortunate here. A1 is AR. All right, let's use a different letter because this is a bit unfortunate. Let's use B. So B0 is A, B1 is AR, B2 is AR squared, right? And so on. So we want to figure out the full geometric series here, right? So the partial sums, the Sn, right, which are, a plus ar plus ar squared plus up to ar to the n. Okay, these types of sums here, which here the sum starts at 0 now, pay attention to that, 0 to n of a r k, right? Sorry. I want to change this up a little bit. This is n minus 1. Sorry, Sn should be the sum of the first n terms. So this is n minus 1 here. Right? This right here is called a geometric series. All right. So what's an example of a geometric series sort of in practice? Well, let's say you have some account that has interest rate R, and A is the principal you put into the account. Then what this amount right here is this is the amount in your bank account after interest, after n minus 1 compounding periods, right? No, this is compound interest, right? So geometric series show up in lots of places. Now, there's a neat trick we can do here. I want to figure out what this geometric sum is, right? Based off that last example we did, if we can find a nice formula for Sn, then we can try and find the limit of the full infinite series, which we call the geometric series. So I'm going to show you a neat trick here. All right, so let me write down Sn. Right, so Sn, a plus ar plus ar squared plus plus ar to the n minus 1. All right. Underneath this, I'm actually going to do something a bit interesting. I'm going to write down Sn plus 1. Okay? Oops, sorry. Sorry, not Sn plus 1. I'm misremembering what I want to do here. I want to write down R times Sn. Okay? This might seem a bit weird, but bear with me for a second. So I'm going to take every term in the sequence and I'm going to multiply it by R. And the way I'm going to rewrite it is when I multiply this by R, it comes down here. When I multiply this second term by R, it goes underneath this one. Right? This one would go underneath here, and so on. The a r to the n minus 2 would come underneath this one, and this one gets to hang out here all by itself. All right? Now what I'm going to do is I'm going to subtract these two equations. Right? I'm going to subtract these from each other. So over here, I have Sn minus Rsn. Right? So it's just this minus this. That's it for the left side of the equation. Let's look what happens on the right side. So nothing is subtracted from the a, but look, when I subtract these, actually I should put this negative around the whole equation here. Right? This is going to cancel with this. This is going to cancel with this. Everything in here is sort of going to cancel with everything below it. This cancels this. And all that's left over is minus ar to the n. Right? So what we get is the equation Sn minus Rsn equals a minus ar to the n. So let's factor what we can. Here I can factor out an Sn. That gives me Sn times 1 minus r. On this side, I can factor out a, and that gives me 1 minus r to the n. All right? And so I can solve for Sn. And there we have it. We did a clever little manipulation here and figured out what's going on. So this is the partial sum formula, right? So now we can try and figure out so let's say question, when does the geometric series right? That's the series from k equals 0 to infinity of a r to the k converge. All right? So when does it converge? And moreover, we can even figure out what does it converge to. So it's going to turn out here that we're trying to take the limit of this Sn here. Okay? So question, what is this limit? All right? Now, if we look at this here, we're going to be able to figure out that actually this breaks down to a simple question, right? So let's break this up a bit. So I can factor out the a. Actually, I can factor out a over 1 minus r, because none of that has anything to do with n. So we're now looking at this limit, right, of 1 minus r to the n. The question is, well, what happens here? Right? And actually, even further, you can break this down to say, well, this is 1 minus limit as n goes to infinity of r to the n. So what does this equal? And the main question here is, well, What is this? What is going on here? If we can answer this question, then we can answer this question. And if we can answer this question, we can answer this question. Right? So we have a nice sequence of questions here that the answer to this is determined by this. The answer to this is determined by this. So let's try and answer that last question. Right? So the answer here, there's sort of three different options, right? Case one, let's say absolute value of r is less than 1. Right? If the absolute value of r is less than 1, then, so in this case, this limit actually has to go to 0. Oops, sorry. Meant to have r to the n. This has to be 0. Okay? So, and the reason for that is, think of like, if r is 1/2, then r squared is 1/4, r cubed is 1/8, r to the 4th is 1/16, and so on, right? So, graph r to the x where r is some number less than 1, okay, and see what happens. All right, so in this case, this would mean the series converges. All right, but before we say more about the series itself, let's look at the other cases that we have here. The next case we want to look at is if r is 1. Okay? So if r is 1, our absolute value of r is 1, that means one of two things. R could actually be 1, right? Then this series is k equals 0 to infinity of, well, a, right? Because r is just 1. So this is a plus a plus a plus a, which is sort of, a times infinity, really. So that means this is going to be plus or minus infinity. All right? So here, the series diverges. Let's look, though, what if r is negative 1? Okay? If r is negative 1, well, then we're looking at a series like this. Right? So this is a minus a plus a minus a plus a minus a, and so on. And what's going to happen there? Well, let's look at the sequence of partial sums. Right? The first term is a. If I add the first 2, I get 0. If I add in the third one, I get a again. If I add in the fourth one, I get 0. And you can see this is just going to bounce back and forth between a and 0 forever. And that sequence diverges. So this here, this diverges. And so the series diverges here as well. Right? So if the absolute value of the ratio is 1, then we diverge. Let's look one more case here. What if the absolute value of the ratio is greater than 1? Well, in this case, what do you think the limit's going to do? All right. So this limit, we'll just say this limit does not exist. Right? This limit does not exist. Really, it's infinity if r is greater than 0, and it actually does not exist like in any way if r is less than 0. right? This would be like looking at the graph of an exponential function and following that off to infinity. That's not going to converge, right? So the series diverges here, right? So the conclusion is that this series, oops, this should be a 0 here. This series diverges if absolute value of r is greater than or equal to 1, and converges if absolute value of r is less than 1. Right? Moreover, oops, that's all one word. Moreover, if it converges, it converges to so this sum here, what is it actually going to equal? Well, we have to go back up here. So if absolute value of r is less than 1, this limit is 0. So if we plug that back in right here, this would become 0, and it's just a over 1 minus r. Right? So this is quite an important fact here. Right? So we're saying a geometric series diverges if the ratio is 1 or if the absolute value of the ratio is 1 or larger, and it converges if the ratio is less than 1, or the absolute value is less than 1.